Welcome to the starting grid, everyone. Think about a Formula One race for a second. The drivers don't just win by pushing the pedal to the metal. They win through absolute, split-second pit crew strategy. Every single second counts. And if you're joining me today, you know exactly what I'm talking about, because you are a focused learner on a mission to conquer the Cambridge Mathematics exam syllabus. Specifically, we're looking at Code 0580, tackling a review exercise for the O-level and IGCSE papers. We all know that exact feeling of pressure, right? You open up a dense exam paper, the clock immediately starts ticking down, and suddenly you are staring down this massive, intimidating mix of conversion graphs, algebraic functions, and coordinate geometry. It literally feels like a race against time. Now, in this race, I see two types of students all the time. First, you have students like, let's call him Alex. Alex overloads his brain with raw mathematical facts, memorizing everything, but applying absolutely no strategy or analysis to how the questions are built. He burns out on lap one. Then you have students like Sam. Sam just rushes. He completely misses the specific command word requirements, sprinting through questions, but bleeding marks everywhere because he didn't read the actual prompt. Today, we're fixing both of those approaches. Passing isn't just about memorizing raw mathematics facts. It's about mastering the underlying strategy and knowing exactly what the examiners are demanding from you. We are going to decode that blueprint right now using real questions. Let's get started.
Okay, let's take a quick look at our track map for today's explainer. We've broken this down into a highly structured, four-part modular approach, so you can completely compartmentalize your revision. First up, real-world conversion graphs. Second, we're mastering mathematical functions. Third, coordinate geometry essentials. And fourth, advanced curves and gradients.
Section 1. Real-world conversion graphs. Plotting your points. Let's hit the track.
Let's start by looking at visual data representation and scaling. Question 1, pulled directly from the paper, gives us a very specific, real-world command. It is given that $100 is equivalent to 56 pounds. Use this information to draw a conversion graph. Okay, so we've got dollars mapping out on the horizontal x-axis and pounds climbing up the vertical y-axis. Now, I want to challenge you for a second. Pause this explainer in your mind and consider exactly how would you set this graph up to guarantee you lock in those full marks without wasting precious time. Because here's the thing, it seems totally straightforward, but students like Sam rush this part. A tiny slip in scaling here, a miscounted square on the grid, and it costs you incredibly valuable points on every single follow-up question. Precision is your best friend here.
Let's break down the exact, foolproof logical flow to secure full marks. Step 1. You absolutely must plot your baseline equivalence. Think about the underlying logic of money for a second. $0 is exactly equal to 0 pounds. There is no hidden fee here. So your very first guaranteed data point is the origin point right at 0, 0. Step 2. You plot the actual data they handed to you in the prompt. You carefully track along the x-axis to exactly $100 and then trace straight up the y-axis to exactly 56 pounds and make a sharp, undeniable mark. Step 3. Because real-world currency converts at a constant linear rate, you don't need to calculate 50 different plot points like Alex might try to do. You simply take your ruler and draw a perfectly straight connecting line from the origin directly through that $100 56-pound point. And this brilliantly illustrates why we use this strategy. For part B of the question, which asks you to convert $64, you don't need a calculator. You just find $64 on the x-axis, follow a line straight up until you hit the graph you just drew, and look straight across to the y-axis to find your exact answer in pounds. It turns a stressful math problem into a totally simple visual lookup.
Moving right along to Section 2, Mastering Mathematical Functions, Working Backwards. We are shifting gears now from visual graphs to pure algebraic functions. Take a close look at questions 2 and 3 here. We are given some very specific mathematical machinery, right? Functions like f of x equals x minus 3 and g of x equals x squared plus 1. These questions are brilliant because they show us exactly how Cambridge examiners test your structural understanding. They always start you off easy with simple, single-value substitutions to get you warmed up, and then boom, they quickly ramp up the pressure by asking you to work backwards to find inverse functions or combine them into composite functions. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get back to tearing these functions apart. Let's quickly reveal the punchy one-mark answer to question 2a, which simply asks us to find f of -5. Our function is f of x equals x minus 3. This is what I call a pit stop question. You need to be in and out in seconds. All we are doing is swapping the letter x out and dropping the exact number, -5, in its place. So -5 minus 3 gives us -8. Boom! That is a fast, easy mark. You absolutely shouldn't spend more than a few seconds here. You substitute the value, you solve the arithmetic, and you keep racing forward to the higher mark questions. Now we hit the real meat of the section. Question 3a, which explicitly asks for an inverse function. Before we even start crunching the algebra, I want to cement this core concept in your mind so you never panic when you see it. An inverse function, which you'll recognize because it's denoted by that little -1 exponent, f to the power of -1 of x, is essentially a mathematical time machine. Seriously, think of it like an undo button. It is a formula that perfectly, precisely reverses the algebraic operation of your original function. If your original function takes a number, multiplies it by 3, and then subtracts 5, the inverse function is going to systematically do the exact mathematical opposite to get you right back to where you started. So, the absolutely crucial point here is knowing the reliable, bulletproof methodology to find it without getting completely lost in a tangled web of algebra. Question 3 gives us f of x equals 3x minus 5. Here is your clear, unshakable three-step method. Memorize this sequence. Step 1. Replace that clunky f of x notation with a simple y. So write down y equals 3x minus 5. Step 2. Literally, physically swap the x and y variables in your written equation. The y becomes an x, and the x becomes a y. It now reads x equals 3y minus 5. Step 3. Rearrange the entire equation to solve for that brand new y. How do we do that? We add 5 to both sides first, which gives us x plus 5 equals 3y. Then, to get y entirely on its own, we divide everything by 3. Our final perfect inverse function is x plus 5, all divided by 3. If you force yourself to follow those exact 3 steps every single time, you will never drop these 3 marks. It's systematic.
All right, entering Section 3, Coordinate Geometry Essentials, Lines and Points.
This is where we bring algebraic equations and the visual grid together into one challenge. Focus your attention closely on question 5 here. The command reads, line L is perpendicular to the line y equals -1/2 x plus 3. Line L passes through the point 8, 9. Find the equation of line L. I love this question. It's a brilliant piece of exam design because it forcefully tests 2 completely separate concepts simultaneously, your theoretical understanding of perpendicular intersections and your practical ability to generate a complete working equation from just one single coordinate point. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's get back to our geometry puzzle. Before I reveal the solution, I want you to actively engage with this. How exactly do we find the gradient of a perpendicular line? Think about the master format of a straight line equation, y equals mx plus c. The m represents your gradient, your slope. If you already know the original line's gradient, what is the exact specific algebraic operation you must perform to calculate the gradient of a totally new line that cuts across it at a perfect, rigid 90-degree angle? This is where students like Sam lose marks by guessing. Don't guess. Recall the rule.
Let's execute the exact sequence. Step 1. Identify the original gradient, which is -1/2. To find the perpendicular gradient, we need to find what's called the negative reciprocal. That sounds complicated, but it just means 2 fast moves. You flip the fraction upside down, so 1/2 becomes 2/1, which simplifies to just 2, and then you instantly change the sign from negative to positive. So our new perpendicular gradient is simply 2. Step 2, now we bring in our master formula, y equals mx plus c. We just found out that m is 2, and the prompt handed us our specific coordinate point where x is 8 and y is 9. We literally just plug all of those numbers into the formula. 9 equals 2 times 8 plus c. Step 3, solve for the y-intercept, which is c. Basic math here, 2 times 8 is 16. So our equation reads 9 equals 16 plus c. Subtract 16 from 9 and c equals -7. Put it all together, and your final perfect equation is y equals 2x minus 7. That is 3 solid marks, beautifully secured by following the system.
Really quickly, I want to contrast those steps with a rapid-fire tip for a slightly different scenario you'll see all the time. Look ahead at question 7a part 2 from this same source paper. It mentions a line M that is parallel to line L. Write this golden rule down right now. Parallel lines, unlike perpendicular ones, share the exact same gradient. If they are parallel, they are locked into the same trajectory. They never ever touch, meaning their slope is absolutely identical. In that specific scenario, do not waste time flipping fractions or changing signs. You just borrow the exact same m value from the original line and move straight to finding the new c-intercept. It's a massive time saver.
Entering the final sector now. Section 4, Advanced Curves and Gradients, Visualizing Equations.
Leaving those predictable straight lines in the rearview mirror, question 6 hits us with 5 different graph sketches laid out alongside 5 very different mathematical equations. They range across the spectrum from simple U-shaped quadratics to complex exponentials and sweeping cubics. This perfectly illustrates the visual density examiners use to separate the top-tier students from the rest. Let me be clear, they absolutely do not want you to spend 10 minutes plugging random x values into a calculator to plot these out manually. That's what Alex would do, and he'd run out of time. They want to see if you intuitively understand the fundamental behavior of curve shapes purely based on reading their highest mathematical powers.
Let's look at exactly how to decode these shapes instantly. Consider the two equations we are comparing on screen. First, the exponential equation y equals 2 to the power of x. Ask yourself, what happens when x becomes a massive negative number? 2 to the power of negative a million. The curve flattens out, getting infinitely closer and closer to the horizontal x-axis, but logically, it can never actually touch it or cross it. That invisible barrier is called an asymptote. That rapidly increasing swoosh that hovers above the line perfectly matches sketch 1. Conversely, look at the cubic equation y equals x cubed minus x squared. A positive x cubed graph has a totally different personality. It has sweeping, dramatic properties. It generally starts way down in the bottom left quadrant and ends up soaring into the top right, featuring multiple distinct turns, or roots, where it forcefully crosses the axis. Recognizing these fundamental behaviors allows you to match the sketch to the equation in literal seconds, saving you massive amounts of time for harder questions.
Now, take a look at this data table pulled from question 7b. We are given a slightly messy equation, y equals x plus 3 over x minus 3. The exam explicitly asks us to complete the data table to help us eventually plot the physical curve. Look at the table. We just have one single missing y value sitting at the very end where x equals 6. This is not a test of complex theory. This is a pure, unforgiving test of calculation accuracy. Students rushing here will punch it into their calculator wrong and ruin their entire curve. We simply substitute 6 into our equation. Y equals 6 plus 3 divided by 6 minus 3. Let's do it mentally. 3 divided by 6 is simply a half, or 0.5. So our equation is 6 plus 0.5 minus 3. 6 plus a half is 6.5. Subtract 3 from that, and it leaves us with exactly 3.5. We confidently drop 3.5 into that final missing box and move on. No panic, just precision.
To conclude our complete walkthrough of this exam paper, I really want to examine question 7b, part 3. It gives a very specific command: estimate the gradient of the curve at the point 1, 1. Here is the massive trap that so many students fall straight into. A flowing curve does not have a single constant gradient like a straight line does. Its steepness is dynamically changing at every single microscopic point along its path. So you cannot simply pick 2 random points on the curve and lazily run them through a gradient formula. It won't work. To find the gradient at the exact coordinate 1, 1, you must manually take your physical ruler and perfectly draw a straight tangent line that just barely grazes the outside edge of the curve at that one exact specific point. Once you have drawn that straight tangent line on the paper, you then calculate the gradient of that straight line using 2 points from it. That is the only acceptable way you estimate a curve's gradient in Cambridge mathematics.
All right, let's take a breath and quickly summarize the overarching strategies we've utilized across all of these past paper questions today. Strategy 1. For conversion graphs, always plot a baseline origin equivalence first to securely anchor your line. Strategy 2. For inverse functions, strictly follow the physical swapping of x and y variables to completely avoid algebraic traps. Strategy 3. For perpendicular lines, always remember the rule to find the negative reciprocal of your gradient. Strategy 4. For complex curves, don't plot points randomly. Visually match the curve shapes to the highest mathematical powers in the equation. And strategy 5. Always remember to draw a physical straight tangent line with a ruler when you are asked to find the gradient on any curve.
As we cross the finish line of today's explainer, I want to leave you with this final, provocative thought. When you sit down under pressure and open your very next mathematics exam paper, are you just blindly trying to recall isolated formulas from memory, hoping they fit? Or are you actually mastering the underlying structural logic that the Cambridge examiners are actively testing you on? True exam mastery comes from understanding the actual mechanics behind the math, not just memorizing the numbers. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep practicing, stay focused, and I will see you in the next session.